The architectural core of modern electrification, from high-torque electric vehicle drivetrains to precision-guided aerospace actuators, depends entirely on the physical performance of heavy rare earth permanent magnets. However, in 2026, the global supply chains securing these critical elements are confronting a harsh chemical reality. Even microscopic trace impurities of less than 10 parts per million can disrupt the magnetic domain alignment of neodymium iron boron lattices, causing premature demagnetization under thermal stress. To hedge against catastrophic component failure and protect multi-billion-dollar supply chain investments, elite venture capital cartels and sovereign defense funds are shifting away from manual wet chemical analysis and investing directly in automated laser-induced fluorescence spectroscopy. The ultimate control over advanced strategic assets is now completely bound to real-time atomic verification at the optical layer. The foundational science of this analytical frontier relies on the quantum mechanics of electronic transitions within lanthanide atoms. Rare earth elements possess partially filled 4f electron shells shielded by outer electron orbitals, giving each element an incredibly complex and highly unique atomic emission spectrum. When a high-energy nanosecond pulse from a ND-YAG laser is focused onto a raw mineral substrate, it instantly vaporizes a microscopic sample, transforming the matter into a high-temperature microplasma. As this plasma expands and cools, the excited ions drop back into lower energy states, emitting distinct wavelengths of light that correspond precisely to the electronic shell structure of the specific elements present. By collecting this light through high-resolution spectrometers, physicists can read the exact elemental barcode of the material in milliseconds without destroying the bulk specimen. The direct financial utility of this laser spectroscopy infrastructure is the complete elimination of fraudulent paper assay manifests in international commodities clearing. For sovereign wealth funds acquiring physical stockpiles of dysprosium or terbium oxide, traditional off-site laboratory testing creates massive settlement delays and exposes the capital to supply chain swapping risks. By integrating automated laser-induced breakdown spectroscopy arrays directly into port customs facilities and refinery output lines, asset managers can execute instant, unalterable chemical audits. The automated systems compare captured optical spectrums against quantum baseline models, immediately detecting trace lanthanide contamination or deliberate filler metal substitution, thereby transforming raw chemical shipments into self-authenticating financial assets traded on hard atomic data. However, operating these ultra-precise laser spectroscopy systems in industrial refining environments introduces severe optical and thermodynamic engineering challenges. The intense heat of continuous laser ablation creates volatile smoke particulates and thermal shock waves that rapidly coat sensitive internal focusing lenses with opaque residue, scattering subsequent laser pulses and distorting the emitted photon wavelengths. To maintain clean optical pathways during continuous high-throughput scanning, instrument engineers construct specialized gas-shielded sample chambers that blast ultra-high-purity argon in a localized vortex around the target area. This laminar gas envelope sweeps away ablated particulates instantly, stabilizing the microplasma temperature and preserving the optical resolution required to detect sub-ppm impurities. This convergence of laser emission physics and strategic material finance marks a permanent evolution in physical asset security. Capital is no longer trusting unverified shipping paperwork or geopolitical promises. It is anchoring its reserves directly to the immutable quantum properties of the periodic table. The corporate syndicates currently financing the mass deployment of automated laser-induced spectroscopy systems are establishing an unassailable gatekeeper position over the fundamental material inputs of advanced technology. The long-term survival of high-tech manufacturing portfolios now depends entirely on mastering the optical signatures of excited atoms, proving that the ultimate guarantor of economic authority remains rooted in the absolute laws of atomic physics and optical spectroscopy.